edition, because second edition is free, right? You can find online. You don't really have to spend money to buy it, all right? If you really have a problem, let me know. I'll send you a PDF file. So let's see, we're going to cover chapter 1, section 3 after 6. Actually, today I'm going to talk about chapter 1, section 2, all right? Because let's just review for functions. Let's just review for pre-calculus. So chapter 2, the whole chapter 2, then chapter 3 up to 5, skip 6, then 7, chapter 4, 2 sections. Oh no, 5 sections. Then chapter 7 a little bit. So you can see it's not a lot, right? It's not a lot. So it's very doable, all right? So what are some concepts, we need to know after this course? We're going to talk about something called limits, limits in mathematics. And we're going to talk about derivatives, so differentiation. Basically 3 concepts for this course, actually. So the first one, we're going to talk about limits, all right? It's a mathematical concepts. Then secondly, we're going to talk about differentiation, how to take derivatives of a function. Then this is all related, some of them are skills, how to take derivatives, and some of them are applications related to rates, maximum, minimum values, optimization. Those are applications, how do we use it, derivatives in life. Then lastly, integration, all right? So integration or integrals, right? That's just different names. Derivatives, differentiation, integral, integration. So basically only 3 concepts, all right? So we're going to take a limit of a function. We're going to take a derivative of a function. And then we're going to integrate a function. All right, so we have to know function very well. So that's why I want to review function today. Now, homework. So homework is this. You have to get it online. It's called lumenlearning.com. Okay, so ohm.lumenlearning.com. The course ID is 46455, and the enrollment key is this. All right, so the syllabus is under the course material or course content. You should download one to keep with you. Okay, grading policy. So grading policy, 10% presentation, which means 10%. What do I mean by presentation? Presentation, first, you have to be present in the class, right? And the second, by ask me questions and by answer my questions. And maybe sometimes I ask, you ask if there's any, if I give you some practice. So after, let's say, after finishing introducing a concept, maybe I go to the homework, which the homework is not online homework. Online homework, you have to do it. We should go to the textbook. So the text I'm going to use after each section, they have homework. So we go to the homework. I ask you to do a couple of them. Then either I call, either I do, I follow the roster, call your name so everybody gets a turn. Yeah, maybe I'll do that. So everybody gets a turn to present your work. Or sometimes homework. Sometimes if I feel, some concept is important to review for the next class. So before I introduce anything new, I'd like to pick some homework, pick some numbers, then ask you to do it. Then, so you take turn. So we take turn to do that. So I'll call your name and to present. Okay, that's what I mean by presentation. So in class, and ask me questions, answer my questions, show your work, show the work I assign. Homework, of course, is this Lumen Learning homework sets is already there. It's online. This is because this is a departmental course, so we have a coordinator and Professor Bendesky. So he designed all the homework and also quizzes. All right, so 20% grades on your homework and 30% grades on the quizzes and 40% final. All right, so we're going to talk about final because the final is departmental. All right, because for now I have no idea how do we do the final yet. We'll see. All right, if anybody has any questions, raise your hand, let me know, or put in the chat. So this is the syllabus. Let me see if anybody has any questions. Okay, seems okay. Do you have to pay for Lumen? That's a good question. If I remember right, there's $25 involved. Yeah, all the homework on Lumen, right, for $150. Yeah, you do have multiple trials. You do have multiple trials, and I think I opened all of them, and also all of them due like the last day of the semester. So you have enough time to do it, but it doesn't mean you have to wait until the last minute to do it. Yeah, the quiz is, oh, let me show you actually. All right, let me just show you. So let's go to Lumen. Okay, this is the website. The website looks like this. Let me start from the beginning. But this is from my end. So we start to use this Lumen website last year. So those are the courses I have taught. But you go into, I'm not sure how many you'll see. Maybe you only see Math 150 2024. This is the one, okay? 2024. So you click in. You see chapter 1, chapter 2, chapter 3, chapter 4, and chapter 7. All right. Then you click here, you open it. They have videos for you to watch, practice. Okay. They have an introduction. Maybe right. Let me go through this because I didn't. So they have a video again. They have this introduction. Maybe they have video again. Introduction of continuity. Video again. Then you see quizzes. Oh, okay. I think those are homework. Those are homework sets. Let me just click one. Let's just click one. See. So videos, you can watch all this, right? They have, let's just click on one. So limits introduction. You can watch. This is very nice. So we bought from Khan Academy. Very nice. So you can even go ahead of me to watch this, right? So when you come into class, you have some idea. You can form some questions. Let's go back. Oops. So now let's click on this. Oh no, that's what just we did. Let's see this one. Estimating limits from graph. Right? Video to watch. Very nice. I think those are the similar things. Those are the videos. Then limit of function. This is homework. Right? This is the homework part. All right. So then afterwards you see, so after the homework, you see quizzes. You have they give you 3 choices, right? So this is first quiz, they give you, let me see how many attempts. 4 attempts, I think, right? So you don't have to do 3 of them, all right? If you do 3 of them, I will give you grades according to the highest grade, all right? If you do 2 of them, I'll choose the best one among 2. But really, you only have to do 1, all right? At least you have to do 1. So I could give you a grade. So each chapter is like this, all right? That's a layout, very useful. So, you know, pay $25, I think it's worth it. If I don't remember wrong, it's $25. So that's the Lumen learning. Let's see, someone has a question. For final exam, okay, right now, because last semester we did online. So everybody has to show their face. Everybody has to show like a 3 square feet area when they take the exam. Let's see for this semester. So take 1 class time, 2 hours to do the final exam. Maybe we'll do the same thing for this semester as well. Oh, Arasa said the Lumen Learning didn't ask her to pay. That's great. It's free. Oh, nice. Education supposed to be free. Great. I think our country is going that way. That's great. Oh, Julia said she had to pay. Okay, I don't know. All right, let's you figure out. All right. Oh, sorry, but it's worth it, $25. All right, now. Okay. Anna is saying you have 2 weeks free trial, or you have to pay $25. Okay, if we have to pay $25, let's pay for it. You know, sometimes pay for education is worth it. All right. So this is about the homework set. So you have to finish your homework. You have to finish the quizzes. Okay, 3 quizzes. You can do 1, at least 1. You may do 2. You may try 3. All right. So that's homework and quiz. So for final, I'll let you know more information. For at this moment, don't worry about it. All right. And surely I will give you practice review sheet for final. Actually, let me try. Actually, let's try to see if they used. Let's see how 1.3. What's going on? Okay, so this video started with okay, this is started with limit. So before going to limit, let's review functions first. So maybe next class I'll show you this. Did I stop? Okay, today let's talk about functions. Okay, my first question is this. Tell me some functions you know. Type in the chat. Tell me some basic functions. Okay, I have here linear function. Good. Quadratic function. Okay, absolute function. What's the absolute function? Oh, okay. You mean f of x equals the absolute of x. Cubic function. Okay, linear function, quadratic function, cubic function are called polynomial functions, right? So they all belong to polynomial functions family. Logarithm function. Okay, log is a cousin with another kind of function. Is the inverse of another kind of function. Anybody know? So when we think about logarithmic function, log function, we should think pair. We should think it's like, we call it do, exponential function, right? So log function, exponential function are brothers, right? They're inverse with each other, which means we can write an equation. If we can write it in log function, we can write it in exponential function. If we can write it in exponential function, also we can write it in log function. Yeah, reciprocal is another word for inverse, right? So reciprocal is multiplicative inverse. Trig function, right? Trig function is sine, cosine. Rational function, great. So we're going to deal with rational functions. Let me see if I can write. Now, second question. Second question is, what is the domain? What is the domain for each function? All right, think about this function we were talking about. Linear function, quadratic function, cubic function, or polynomial function. What is the domain of polynomial function? Yeah, domain talk about the x value. What are some possible legal x values for polynomial function? All real values, right? Raphael, thank you. All real values, right? Basically means there's no problem. We can plug in any real number to the function to output another value. All right, so the second kind is someone mentioned. Let's talk about exponential functions and the log functions. Remember exponential functions, f of x equals to sum a times sum b raised by x. What's the domain of exponential functions? All real numbers, right? X can be any number because x is the exponent of b. But what about the log functions? Let's see, f of x equals to a times log of, let's say, cx plus b. A, B, C are not the variable, right? Even it looks like a variable. But because my function is in terms of x, so we're treating A and B as numbers. Only x is a variable. Right. So can anybody tell me what's the domain of log function? So for exponential function, the domain is all real number, but not the same thing for its inverse. Its inverse is limited. Oh, actually, let me try not to use cx plus b. So let me just make it simpler. So let's see, just equals log x. Log x. So the domain for log is x has to be greater than 0, right? X has to be a positive number. If you remember the graph, if I have a coordinate here, the graph goes this way, right? So if this is my y-axis, this is my x-axis, the graph goes this way. X value never goes to the opposite, never goes to 0, never goes to the negative number. All right, so that's one limitation domain. That's one of the functions. The domain is not a real number. What about rational function? Let me give you an example. So f of x equals to 1 over x. What is the domain of this function? All real numbers except 0. Great. Now let me give you another function. Equals to 1 over x minus 1. What's the domain of this function? All real number except 1. Great. All right. So now because for certain functions, the domain is not all real number. That gives us some limitation for the domain. So then when the value is not in the domain, in the graph, that gives us a vertical asymptotes. So this is from this point to this point. This is a continuous function. So the notation of this empty circle means this value is not in the domain. Right? Solid circle means this value is in the domain. Right? So if we use a notation for this, we see the domain. I want to write here what's going on. Why okay. So let's see this. If we call this A, if we call this point A, if we call this point B, so this is just a notation. Notation we're saying the domain of this is open parenthesis, A, comma, B, close parenthesis. All right, I should use this one. So domain for this function.
Professor, are you sharing anything? Because we can't
Can I see it? Yes,
No, we
I
don't see
am
it.
sharing. Oh,
We
it's
just see the textbook.
that's interesting. Okay, hold on a second. Let's see. Why I have 2 pages? Oh no, this is wrong. Can you see this textbook?
Yeah.
Okay, functions and limits. Oh, actually, I can go back to check. Oh yes, now it's right. Yes, I was writing on a different page. Thank you. I opened too many in my browsers. Now, okay, let me see the question. Oh, okay. Yeah, we're reviewing functions. What's going on? Oh. Sorry, I clicked on the wrong button. Okay, now we should be in the right place. So you're seeing this textbook, right?
Yeah, we can see the textbook.
Yeah. Oh, I see all your names. So somebody is worrying about attendance. All right, I see everybody. So here, right, I see everybody. I have 37, so I only have 3 students missing. So don't worry about the attendance. I'm not going to check because I have all your names here. All right, I need to go to the view file because I cannot move here. Oh, yeah. Yeah, thank you. Let me know if anytime you don't see anything. Okay, so I'm going to suggest you to do this. Okay, so this is diagnostic test. It's all about algebra. All right, so calculus, we need to have a strong algebra skills. You know, usually I like to see mathematics only have 2 families, equations and expressions. Right? With the equations, one big family is functions. With expressions, we always want to simplify it. So these are some simplification tests, all right? So try this. So this will be your, optional homework. So go through this diagnostic test to see if you can do all this algebra. Let's see one of this, right? Factor each expression. You have to be able to factor this expression. You use the difference of square. The first one using difference of square. The second one, you group them. You group those two, then try to find the common factor. And number five, simplify this because each one is a rational expression, right? Because we see x in the denominator. How do we simplify it? We want to factor the numerator, want to factor the denominator to see if they have common factors. Okay, go through this. This one is called a rationalized expression. Let's B, right? We can rationalize the numerator. So what do? We use difference of squares. We multiply by its conjugate. Its conjugate is plus 2. It's the first term plus 2. When we multiply, we get the first one square, second one square. We get rid of this square root. All right. So So try this diagnostic test. They even show you answers. All right. So go through that. Geometry, right? If you can do this, wonderful too. All right. Great. Right. Go through this diagnostic test. All right. Functions. Beautiful. Let's see number 2. Let's go through one because functions are super important for us. Calculus is built upon functions, so we really need to know functions well to get into this class. So this is a graph, right? So function can be represented in different ways. It can be represented as a set of ordered pairs, right? Each one has x value, has y value. Or function can be expressed as an algebraic expression, or function can be graphed, right? So this is a function. And when we talk about limits, we use a lot about the graphs. All right, so go through this. So what is the value of f of -1? That means the function, the x value is -1. So we go to the graph, we find a value for x, -1 right here. This is the -1 value, right? Then what's f of -1? We go to the graph, right? We go to the graph. Oh, here f of -1 is -2. So on and so forth. Or let's see 3. 3 is the same, the function value is 2. Then what's the variable x? So we go to the graph to see where is the point y value equals to 2. That's right here. So then f of x is 2. What's x? X is 1. Right? So very basic. Then number 2, evaluate. So we're given a function x raised by 3, cubic function. We want to evaluate this called difference quotient. We're going to difference quotient. The limit idea will be using this difference quotient. So we need to be very good at calculating this. But if we know the function is x cubed, what's f of 2 plus h? That would be 2 plus h raised by cube. Right? Because here function is defined as x cubed. So f of 2 plus h equals to 2 plus h raised by 3. So we just substitute, right? So we check the function, we substitute the variable. The variable x is given as 2 plus h here. Then subtract f of 2. Right? F of 2 is just 2 cubed. Then do the calculation. Okay, find the domain of the functions. Right? We have to factor this denominator. Let's see how do we factor this one. So I'm only going to factor the denominator, all right? So x squared plus x minus 2, we can factor it as x. Oh, this one is not so easy. Oh, it's easy actually. Okay, x plus 2, x minus 1, right? Because the middle term is plus 1x, the last constant term is negative 2. So we factor it as this, right? X times x. So we check, oops. X times x, I won't be able to do that. Oh, here. X give us the first one, x squared. Then x times negative 1 give us negative x. Then 2 times x give us 2x. Add together, we get positive 1x. Then 2 times negative 1 equals negative 2. Okay, if you are not very good with the factoring, practice on this. So once we factor this, we know this is in the denominator, right? In the denominator, we know we cannot make the denominator 0 anytime in mathematics. So when will this denominator will be 0? When x equals to negative 2, when x equals to 1. So what's the domain? The domain is all real numbers except negative 2 and positive 1. And on the graph, we will see 2 vertical asymptotes at negative 2 and at 1. So the graphs will be separated with this asymptote, vertical asymptotes. The graph may happen somewhere, right? Then stop either going upward or going downward, we don't really know. And also inside, we have a branch inside. Then we have a branch outside. But the graph will not be continuous, not like this. This is one piece of string. We call this continuous. This function is continuous from this point to this point. Rational functions, except sometimes rational functions usually not continuous, except some special situations. But you can simplify it to be some polynomial functions. Then we will have a circle. But even though we still have vertical asymptotes. Okay, so rational functions, right? So we have this vertical asymptotes, and those values not in the domain. And then we want to talk about, so we won't be able to talk about There's a function value at those points, because those points not in the domain. That's the beginning of the idea of limits. So we need something else to talk about a situation like this. So then we'll introduce the concept of a limit. Okay, let's keep going. Okay, make sure you can graph. You can graph polynomials. That's a rule for graphing polynomials. But make sure you can graph log functions, trig functions, exponential functions. Okay. Yeah, great. You see, that give you answers. Compositional functions, a degree and radian, trig functions. Okay, right. If you want to, if you are math majored, physics majored, computer science majored, you want to be really good at math, try those diagnostic tests. Okay, make sure you can use them. Okay, so anytime you can throw me questions anytime. All right. Otherwise, I'll just mumble along. Function and limit. Anybody has any question?
No, thank you.
I heard a little bit of noise. All right. If you have a question, stop me anytime. Okay, let's keep going. You see this word limits. Okay, so today I want you to remember this word limits. Right. So functions we know. Functions, right, either continuous or not continuous at a certain point. We'll talk about at a certain point. You see this function is continuous, right? From 0 up to this point. Let's see this function. This function is not continuous at all, right? It has a function value at 0, has function value at 10, has function value at 20, but then in between of 0 and 10, there's no function value. Right? Same thing from here to here. We have one piece of string, always continuous function. Oh, this is not a function, right? This fails vertical line test. If one x value give us two y value, give us two function value, that's not a function. It's a certain relation, but it's not a function. Okay, now let's take a look at this function. This function is not continuous, all right? So what is the domain? The domain is from negative infinity up to 1, right? I won't be able to type negative infinity. Let me just use a word. Up from negative infinity up to 1 with a bracket. Because 1 is in the domain. Then union another one. Then 1 is not in the second domain up to positive infinity. Right? That's the domain of this function. Assume this going forever. Assume this also ever goes forever. So this shoots away, this shoots away, assuming that. So we see this domain is divided into two parts. Right? On the left of 1. On the left of 1. So this is left. Right? and this is on the right.
Excuse me, for the square
Yes.
bracket,
Yeah.
why did you not, I just need to familiarize myself with this for a second. Why did you not put the
Great.
square bracket for the positive one?
You mean the first one, why I use bracket instead of open parentheses, right? Close
Yeah.
parentheses.
Yeah.
Okay, great. When we have this, you see the second one, I use open parentheses for 1. Do you see this open circle here?
Mm-hmm.
Okay, the open circle means the value is void. It's not there.
Oh, okay, I remember. Okay, got it. Thank you.
Okay, that's just a notation. Bracket means 1 is included in this set, in this interval.
Yes,
All right, so,
it's,
okay, so
it was the greater or equal to and then greater less than.
exactly, yes, equal to, with equal sign. But for this book, we're going to use this notation. So then, so 1 is not in the domain, right? 1 is not in the domain. Because, I mean, I cannot say 1 is not in the domain. 1 is in the domain of the left. 1 is not in the domain of the right. And the function is not continuous. Function is not continuous. Okay, then we need something else to explain the situation, to carry on the mathematical structure. So what do? We invent the words about limit. So we will talk about, okay, I can, really, the function value of f of 1 exists for this first part of the domain, but does not exist for the second part of the domain. So the domain being cut into 2 parts, 2 disconnected parts. So then we can talk about the limit. So limits, we simplify using just LIM. Limit of x on the right-hand side of x. So we'll use x approaches to 1 from the left. We use -1. So we put 1 raised by negative, just negative sign. Let me write this. This is better to write. So we're using the notation limit. So imagine this is a word of limit. Then on the bottom of it, we write x approaches to 1 from the left. We put a negative sign on top of this 1, on the top right hand side of the -1. You'll see later in the textbook, right? So that means we can think how the function, what is the behavior of this function when the x value approaches 1 from the left? Well, what happens? And we can write here that equals to 0. So the left limit of 1 to come from the left of 1, the value is 0. It's not function value. Okay, limit x approaches -1 approaches to 0. Similarly, we can write the limit x approaches to 1 from the right. Well, what happens from the right? The function value approaches to 1. So if we write the limit x approaches to 1 plus, think about plus means a value a little bit bigger than 1, minus means a value a little bit smaller than 1. That equals to 1. So the 2 limits are not equal, right? One limit is here, one limit is here. So 2 separate domains give us 2 limit values for the same point. So we conclude to say, okay, the limit does not exist. At this point, I just want you to know limit is a new idea. It's It's a new structure, right? Just like we have built different function models. We talk about domain, we talk about range, and we talk about the continuity of a function, right? So now limit is another structure of it, just another concept of math. It's limit. Why do we need a limit? Because of situation like this. Because at a certain point, we have a situation we have to deal with. Well, let's talk about what about other points for this function. Let's see, what about point here? Let's see, maybe -1, right? Do we have a concern x value to be -1? No, right? We have a function value, and the function is continuous at this point, so -1 does not cause any trouble. So the limit is defined for dealing with those values not in the domain, right? But of course, we can talk about the limit of x approaches -1 from the right, from the left. They will be the same. They will be the function value. So basically, there's no point to talk about it. So the invention of limit is to deal with situation like this. All right, this is saying, this is confusing. How am I going to talk about the function value f of 1? Right? This domain is separated into two parts. On the left of the domain, the function value is here. But on the right, there's no function value, the open circle. All right, so limit ideas for this. Any questions? If you have questions, maybe we're going to talk about more about this. Let's see for this function, absolute value function, right? Someone mentioned earlier. We see this is a continuous function, right? This is a continuous function. But later on, we're going to talk about it's continuous, but it's not differentiable. Remember 3 big concepts for this course? We're going to talk about limits. We're going to talk about differentiation. We're going to talk about integration. So absolute function, continuous, but only the vertex is not differentiable. We'll talk about that later. I just want to give you some impression for this. Let's see, someone has a question? When the limit doesn't exist, does that mean the function is definitely not continuous? You are right. Yeah, that's a great point. Yes. Let's just see here. Let's just go back. So continuity, right? Continuity, we see from 1 up to -infinity, that's continuous. The function at the left domain is continuous, and the function on the right domain is continuous, but it's not continuous at 1. So we use math language precisely to see the function. So f, let me just use f of x to represent this function. Okay, whatever this function is, f of x is not continuous at 1. Okay, we're not saying the whole function. The function is continuous at every other real number but 1. So we say f of x is not continuous at value 1. All right, keep going. Does the open circle mean continuity will end always or sometimes for any graph with limits? Well, this is a very good question too. Let me give you an example. This depends. But let me see if I can find. Now let's go back to this. Just pretend we define a function. We'll see this.
Isn't an example of that the continuous line with the open circle in the middle?
What do you mean in the middle? Well, the open circle can be anywhere. You mean like this?
When you're graphing the continuous line and and it includes one point, but it doesn't include the other. Yeah, and it's like a linear line.
You mean when those two fall together, like this?
Yeah, but it's a straight line. Yeah, basically.
Yeah. Yeah, those are different situations where I was about to write in mathematics algebraic expression, but let's use this graph. Yes, you're right. Let's see. If the function on the left-hand side include 1, and the function not include 1, however, the two functions overlap at 1, do you see one piece of string? So that make it continuous. All right. So it's not definitely one with open circle, one with bracket means the discontinuity. No. If the function happens to overlap at a point, that will make a continuous function. So that's a special situation like this. All right. Okay. Okay, now let's see this step function. Step function usually for probabilities. Let's see, from 0 to 1, we see 0 is not in the domain, right? 1 is in the domain, so we won't be able to talk about f of x, f of 0. Right? F of 0 is not there. And here, we can talk about f of 1. F of 1 on the left, on this domain, we have function value. But in this domain, we do not have f of 1 value. The step functions. So those discontinuous functions at one discontinuous at 0, at 1, at 2, at 3. If we use the limit idea, we would say, okay, limit does not exist at, let me write here. Limit does not exist at x equals 0, 1, 2, 3, 4, maybe so on and so forth. Right? Because we do not have left limit. When limit exists, that means the left limit and the right limit agree. Take a point of 0.5. Right? 0.5. Left limit goes to this value, maybe 0.85. From the left goes the value, from the right also goes the same value. So the limit exists, and also the limit equals the function value. Sometimes we will see another situation, the limit exists, but the function value is not the same. So the math language is to describe this situation. We see limit does not exist at x equals 0 at 0 value, 1, 2, 3, 4. This is all continuous, right? One piece of string, polynomial functions, one piece of string. Okay, it's worth it to do this one. All right, so I'm going to assign you this as a homework. 21, page. Oops. Let's see which page is this. Page 9. So this is the second edition of Stewart book. Okay, 21 to 24. All right, 21 to 24. So this is like an optional homework. But however, I use this optional homework to give you grades for presentation. Let me
Question: if we take the diagnostics test, would you credit that as well?
That's for your own good.
Okay.
Yeah. Optional homework 21.
Hello.
Yes. 21 to 24.
How will we submit this homework?
Oh, you don't have to submit. This homework
Oh,
is for me, right? To call people. in the class to present. Remember the 10 point is presentation?
Yeah.
Yeah,
Okay, thank you.
you're welcome. Okay, so this is optional homework. All right, try this. And anything, you know, I emphasize on will be on your test, right? And will also will be important because the limit, we need to do this calculation. The limit, the definition of limit is built upon this difference quotient. This word, difference quotient. Oh, this is annoying. Why? Difference quotient. So this is called a difference quotient. A catalog of essential functions we talked about in the very beginning, the linear function, any polynomial function. So this is a polynomial function, right? The a sub n, all the a's represent a number. So the variable is x. This is nth degree polynomial, right? Linear function is 1 degree polynomial. Quadratic, the 2 degree polynomial. And constant is a 0 degree polynomial. Cubic is a 3 degree polynomial, so on and so forth. All polynomials are continuous. You know, there's no need to talk about to use the idea of limit because you know every real number is in the domain. We don't have to talk about what happens from the left or what happens from the right, right? Because the limit exists equals the function value. Well, let's see this one. Later on, right, someone is asking, are we going to use the limit definition for derivatives? Yes, that's further away. Specific function never have limits? It depends. What do you mean talking about never have limits? Because limit is not idea, right? You can use limit for any function. But the only thing is, we talk about limit at a certain point. You could see limit, you know, exists or does not exist depends on the
relationship, right?
Depends on the functions. We can always talk about limit of a function. We can always talk about that. It just, you know, either exists at a certain point or not exist at a certain point. Basically, we'll see 3 situations. We'll conclude with 3 situations. But now let's observe this function. This function, this is rational function, a typical rational function. So what's the domain of this function? X cannot be -2, so -2 and 2 not in the domain. Right? So that means those 2 points, -2 and 2, cause trouble for this function. Okay? We see difference of squares. The denominator we can factor as x plus 2, x minus 2. So that's why -2 and 2 not in the domain. Not in the domain means we won't be able to talk about f of -2, f of 2. We don't have, right? So we don't have f of -2. We won't be able to talk about f of 2, f of -2, right? Because there's no function value. Because the -2 is not in the domain, 2 not in the domain. So what can we do? We want to use the limit idea, right? We want to say, okay, what's the limit at -2 from the left? What's the limit from the right of this? So we use a notation. We say the limit, right, f of x. Then at the bottom, usually we write smaller. X, oops. f limit followed by f of x. Then the bottom of red x approaches to limit of f of x, x approaches to -2 from the left. Okay. What's that? Let's observe. So that means where is this function heading to from the left of -2? Do we see positive infinity? Right, positive infinity. Oops. We read this way, all right? We read the limit of f of x when x approaches -2 from the left equals to positive infinities, because we see this shooting up. What about on the right? The same way we write, but this is heading towards negative infinity. So that's why those two limits, the left limit, we call this left limit. We call the plus -2 raised by plus right limit. Left limit and right limit do not agree. Great. All right. But you answer my question is great. So then we see the limit does not exist. Okay, the function is not continuous at this point at -2, and the limit does not exist. Similarly for value 2. So this is one situation. So this is a similar way, right? We see at the -3 pi over 2, at the negative pi over 2, at the pi over 2, 3 pi over 2, we see these vertical asymptotes, means those values are not in the domain. Not in the domain, so we can talk about from the left of this value limit, and from the right of this, from the right of this value. What about the limit as x approaches 0 and an infinite acceleration function like y equals the sine 1 over x? That's a great question. We will see the graph, all right? It accelerates. You know, even we cannot see through our eyes, but when we do a simulation on the computer, we see at the 0, this is called a scientist's curve. This is a typical function, and the limit does not exist because the left limit and right limit always jumps up and down when it gets close to 0. Does not exist. So when the left limit and the right limit do not agree, they have to agree on one point. Then we see the limit exist. If they do this, no, they do not agree. The limit does not exist. Okay, now I think we're ready for the limit. All right, we're ready for the limit. So the limit of a function. This is the same. We can use this table value, right? If we want to talk about what happens at, I don't want to use this example. This is basically, you assign x, a value approaches to 2. You go from 1.0, 1.5, 1.8, approaches to 2 to see what happens with the function value, right? For any polynomials, let's say this example. Before someone asks, can we talk about limit for any functions, right? We can talk about limit for any kind of functions, even for polynomial functions. But what happens with polynomial functions? Let's see this one. This one is saying, consider x value to be 2. What's the limit of x approaches to 2 for this function, for this quadratic function? Well, we know quadratic function, and this quadratic function happens to be upward parabola, right? When x equals 2, somewhere here, what happens? It's continuous. 2 is in the domain of this function. So what's the left limit? The left limit equals to 4. What's the right limit? The right limit equals to 4. What's the function value? The function value also equals to 4. Right? So it's a continuous function. So continuous function has these 3 things agreed. Left limit, right limit, and function value. They are all the same thing. So that's a continuous. All right, so we can talk about limit of any function, right? From the left, from the right. If a limit exists, what does this notation mean? This notation, this is so annoying. This notation means the left limit equals to the right limit, right? We only see 1, so this means the limit exists. So limit exists. Limit exists means, approaching from the left at a certain value, approaching from the right at a certain value, they're heading to the same spot. They head to the same spot. So limit exists. If it exists to a value. So that's the definition. You see, this is a continuous function, right? Pick any point. Pick this point. The limit comes from left equals to this function value. The limit from the right also equals to this function value, and the function value equals to the left limit equals the right limit. So at this point, the function is continuous. Now let's see this one. X squared minus 1, the denominator is x squared minus 1, but then we can simplify. We simplify, that's right here. So we can rewrite this function as x minus 1 divided by x minus 1. We factor the denominator, x plus 1. So we factor out the denominator. Then we see we have x minus 1 divided by x minus 1. They simplify the 1. Simplify, then we get 1 over x plus 1. So this function becomes 1 over x plus 1. But still, so what's the difference between those two functions? This function is saying 1 and -1 not in the domain. So -1, 1 not in the domain. Let me use big B. Hold on 1 second. Okay, sorry, someone buzzed my door. So this is the original function, right? The original function is saying -1 and 1 not in the domain. But what about this simplify? After the simplification, looks like 1 is in the domain, -1 is not in the domain, right? That's the difference. So these two functions, the difference of this original function and the simplified function is this. However, when we graph, what do? We still have to make an open circle for 1. Let's see the graph. We still have to make an open circle for 1. You see this one? It's the open circle. It still means 1 is not in the domain. right? Then we can talk about limit of this. So what happens? So the function value is not there. We won't be able to talk about f of 1. Right? We won't be able to talk about f of 1 because 1 is not in the domain. So we talk about the limit. Let's go from the left. The left limit equals 0.5. Well, how do we get it? Going through this table. What about the right limit? Actually, we can go through the after simplification, right? So in here, we have no problem to plug in x equals to 1 after simplification, right? So from the left, we can evaluate. From the right, we can evaluate to get 0. We get a half. So this situation is different, right? Remember, we have the first situation. Let me make a list here. First situation for continuous function, f is continuous, means this. Means the left limit equals to right limit equals to function value. Function value, I mean f of x at x equals to a certain point, right? So I should say this, I should be precise. F is continuous at x equals to 8. Let's give a value. Means left limit when x approaches to a equals to right limit when x approaches to a equals to f of a. Right? So the first situation, when f is continuous. When f is continuous at certain point, the left limit of the certain point equals the right limit of the certain point equals the function value. All right. So this is the second situation. The second situation is saying to left limit equals to right limit, but not equal to f of a. All right, I'm going to use the same setup for the first one. Okay, so that's this situation. All right, that's this situation. You see the function value f of 1 is not there. Right? We won't be able to talk about f of 1. F of 1 does not exist. Does not exist. It's the open circle. Open circle means it's void. But the left limit approaches the half, the right limit approaches the half, so the limit exists. So we see this one, so the second one, limit exists. Function is not continuous. Limit of f at x equals to a exists, but not equal to, that means left limit equals right limit, but not equal to f of a. And if this is the case, like someone mentioned before, this means f, let me write another one. This means f is not continuous. So f is not continuous at x equals to 8. Second situation, okay. The first situation we don't need the idea of a limit. Okay, if the function is continuous at a certain point, all three things are just one thing, just a function value. The second situation is the limit exists, but it's an open circle. The value is the x value is not in the domain, so we won't be able to talk about the function value. So that means that even the limit exists, but the function is not continuous. All right, that's the second situation. And we have one more to talk about, one more situation to talk about. This is a sign. This is another one. This is an important identity. All right. Oops. Can use this. All right. So this is important identity. Okay. If you cannot remember all at once, write 10 times and use it for your homework. So this is saying the graph is this, sine x over x. All right. We can see from the graph. The left limit approaches 1, the right limit approaches 1, but not equal to function value because of the open circle. Okay. So we use this as an identity, all right, as a rule, as a theorem. We use this for free. Sine x over x equals 1. And we can flip over. If we flip over, it still makes sense. Basically, this theorem should be parentheses raised by, let's see, raised by z. Z means an integer, okay. Raised by any number. Let's see, raised by k. So remember this theorem as this sine x over x raised by k. Okay, so this is parenthesis. Please, okay. K can be positive, K can be negative, all right? But K cannot be 0. K, let me see, K is an integer. Any integer, all right? So if you have a sine square x divided by x squared, the limit when x approaches 0 also equals to 1. So this identity is very useful. Let's try to use the identity for this. The book is saying conclude identity equals 0. But let's try to use this, the book approach this way, but let's try to use this identity. This identity is sine of the angle divided by the angle when the variable goes to 0. Okay, the variable goes to 0 here, right? So we have that. We have a sine of pi over x. So the angle is pi over x. So what do we have to do? We just have to multiply 1. And this 1 is pi over x divided by, I should put a parenthesis, divided by itself. Right? This is 1, right? Even it's 4 layers of fraction, so pi over x. So we want to multiply pi over x divided by pi over x because we want to use this identity. We have sine pi over x now divided by pi over x. Actually, it won't help much. Let me see the question somewhere in the typing. Oh, okay. Well, okay, let's use this time to talk about using group. Yes. Yes, right. We should make groups to study. And yeah, that sounds great. Right. Do group study. Right. Now, let's go back. Let's go back. So then what's left? Then we have limit. Okay, then what's left? We have, so sine pi over x divided by pi over x, according to the identity equals 1. Now we're left with the limit of x approaches 0, pi over x. So, oops, then we have to consider. So now we only have pi over x to consider, right? So what's the limit of that? If we think about f of x equals to 1 over x. So because pi is a constant number, right? So think what's the limit of 1 over x? And remember the graph. What's the graph? The graph is the graph of 1 over x. We have one part over here, or another part over here. All right? At 0, from the left-hand side, the left limit goes to the negative infinity. The red limit goes to positive infinity, so the limit does not exist. All right, so the conclusion for this one, the limit does not exist. If someone asked earlier, sine 1 over x or sine pi over x, pi is just a constant number. Okay? So this is called scientist's curve. It oscillates at 0. But we can use identity, okay? We can use this identity. Whenever we see the function involves trig functions, we're trying to use this identity. So this identity is very useful. Sine x, so inside parentheses, the sine x over x, this is raised by k. K is any integer. So the limit does not exist for this one. Right, that's the conclusion. Okay. So we talked about two situations. We talked about the first situation, function is continuous, left limit equals the right limit equals the function value. The second, limit exists, but it's not equal to the function value. So the third situation will be the limit does not exist at a certain point. So let me write here as a 3. Right, we see the left limit. So left limit of this, what's the left limit? 0, right? So I'm going to write LL to the left limit. Left limit equals 0 for this case, and right limit equals to at 0. Okay, at 0, because this is the only problem for this function, right? From 0 up to negative infinity equals 0. From 1 up to positive infinity equals to 1. So it's a constant function. So the only problem is at x equals 0. So then the right limit equals to 1. So we see the limit does not exist. They do not agree. The limit of f of x does not exist at x equals to 0. If limit does not exist, right, we won't be able to talk about, are they equal to the function value? We won't be able to talk about continuity. All right, as long as the limit does not exist, we know the function is not continuous. Okay, let me see. Someone has a question or comments. We can use limits to talk about end behavior. Great question. Great question, Raphael. Let's see the end behavior. Yeah. Yes, that's a, we could, of course we talk about that. Could use that, right? Okay, so that's the third situation. I think that's it. The three situation. Yeah, it covers about the situation for limits. The first one is a limit exists if the function is continuous. Left limit and right limit agree, so limit exists, and even equals the function value. The second situation is the right limit and the left limit not agree with each other. So that means the limit does not exist. Oh, no, the second situation means the left limit and the right limit agree. They're same number, but they're not equal to the function value. So limit exists, does not equal the function value, so this function is not continuous at a certain point. The third situation is left limit and right limit do not agree. For this case, left limit is 0, right limit is 1. The left limit and right limit does not agree, so the limit does not exist at 0. The function, of course, is not continuous. Okay, I have a question saying why the right limit is 1. The right limit is 1 because of this. Okay. Yeah. Okay, from the left, right, when it approaches 0, we see 0. From the right, do we see here? Approaches at 0, it approaches 1. So that's why the right limit equals to 1, right here. Right, from right, on the right-hand side. Imagine it comes this way, right? Approaches to 0, the function value, the right, approach to 1 actually is a function value. Yeah, that means, right, solid value means is a function value. So in this case, we're able to talk about function value. Function value exists at 0. What's f of 0? F of 0 equals to 1, and which we could see equals to right. But as long as right limit does not equal to the left limit, we conclude the limit of f of x does not exist at x equals 0. All right, the function value, yes, exists, but it does not mean the function is continuous. No, it could be different situations. We see 3 situations, right? So this question is, will every function with a limit always have a solid or open circle, or does it depend on the case? It depends on the case. Depends on the case. You see here, we do have a function value, right? Equals to the right limit, does not equal to the left limit. But see this one, you see this one, the left limit equals right limit, but the function value is not there. The function value is not there. And sometimes we may have a situation like this. This may also be an open circle as well, right? This may also be open circle as well. If this is an open circle, that means we won't be able to talk about f of 0. Depends on case, different cases. So I already mentioned the one-side limits. So we can talk about x approach to a from left. We call this a left limit. We can also talk about f approach to a from right. We call right limit. Plus is a plus sign here. So a raised by negative sign means think about a value a little bit less than a, right? little bit less than A. So that's the approach to A from left. A plus means think about a value a little bit bigger than A. That means from the right. All right, let's see this graph. This graph covers all the situations. Let's talk about A. So this is saying X approaches 2 from left. So let's see, 2 is right here. Right? So we look at X value equals to 2. We think, well, can anybody tell us what's the left limit of G? 3. Yes, left limit means this. We look at this left part of the graph. Left limit is 3. What about right limit? 2. Right, right limit is 2. What about the function value? Are we able to talk about f of 2? Is f of 2 there? We see 2 open circles. No. So at x equals to 2, so let me write here. So equals to 3. Oops. And the right limit equals to 2. Oh no, equals to 1. Sorry, it's not a 2, it's 1, okay? It's the left limit right here. The right limit is 1. So the left limit is a 3. But looking at here, the y value, okay, basically we're looking to the y-axis, right? X equals 2 from the left, we look this, 3. X equals to 2 from the right, we look this, equals to 1. So how do we conclude C? What do we have to say about C? The limit of G when X approaches 2 does not exist. All right, because left limit and right limit do not agree. So C, we see the limit of G when X approaches 2 does not exist. Okay, now let's go to 5. 5 is here. Let's look at from the left. From the left, we look at the graph. From the left, A equals to 2. Over from the right, also equals to 2. So what do we conclude with the limit of G when X approaches 5? Yes, they do agree. So we conclude that equals to 2. Okay. All right, let's see the difference so far. So when X equals to 2 at this point, the left limit equals to 3. The right limit equals to 1. They do not agree. So we conclude the limit at x equals to 2 does not exist. The second point, 5. The left limit equals to 2. The right limit equals to 2. So the limit does exist. And the limit when x approaches 5 equals to 2. But what can we see about the function value? What is f of 5? Do we see f of 5 equals like maybe 1.2 or 3? Right? You're right. Does not equal the function value. So we see the function value. Where do we find the function value? The function value is right here. We see a solid dot here. That's f of 5, right, is solid dot. F of 5 equals to about 1.3, 1.2, something like that. Okay. So the limit does not equal to, I won't be able to do that. So not equal to this, the function value. So even the limit exists, but does not equal the function value. So the function is not continuous at this point. So here, so far, we see that f is not, no, g. So g is not continuous at x equals to 2 and 5. Right? So those two values of x, 2 and 5, give some trouble, right? At 2, the function is not continuous. At 5, the function is not continuous. All right, any questions? Okay, if no question, we keep going. 1 over x squared, the graph goes this way, right? It's good to remember some graphs. 1 over x is one branch here, one branch in the third quadrant. But when we square it, the negative part becomes positive, so it's being flipped over on top of x-axis. So this is a very mathematical idea. I use epsilons and the deltas to talk about the limit, but it's not. But we're not using for this course. All right, now we have about 10 minutes. Let's see. So this one, two. Okay, let's pick this one. Let's pick this one. So let's pick this graph, all right? Let's do this graph. So I want you to consider the situation, consider x equals to or 0. The first one to consider 0, then 2, 0, and 2, 0, 2, and then maybe another one, 4. Let's see, 4. All right. Try this on your own. Okay, write down on a piece of paper. So I'll give you like 3 minutes to figure out the left limit at 0, right limit at 0, function value at 0, left limit at 2, right limit at 2, function value at 2, left limit at 4, right limit at 4, function value at 4, then make a conclusion about these 3 points, all right? Four is here, right? Or let me not mark anything to confuse you. If anyone finished, let us know. Can we go over a problem using the theorem? Let's see if we have time. Great. Okay, let's go over this quickly. All right, let's see at 2, at 0. The left limit equals to -1. The right limit equals to -2. So the limit does not agree, but the function value agrees with the left limit. At 2, the left limit equals to 2, the right limit equals to 0, and the function value is 1. So 3 of them do not agree. What about at 4? The left limit is 3, the right limit is also 3, and the function value is 3. All right, so this covers the 3 situations. Let's see, anybody has any question? Right, Raphael tapped in this. Raphael, what do you mean limit when x approaches 4 equals to infinity? No. Let's take a look. At 4, 4 is here. You're talking about n behavior, right? You're talking about this goes on forever, right? But I'm talking about at 4. At 4, you see right here, right? Look at the graph. From the left, the limit approaches from left is 3. The limit approaches from the right is also 3. And the function value is 3. Because at this point, 3 things fall together. So it's continuous at 4. All right, good. Now let's see. Let me find one to use identity. Because when sine x over x equals to 1. This takes a little time. Let's use this one. Let's see, check 16, right? Let's check out 16. 16, we know tangent 3x. Okay, first hint, x approaches 0. If x not approaches 0, we won't be able to use identity. The limit, consider x approaches 0, so we have check functions. We're thinking to use identity. So tangent, what's the angle? The angle is 3x. What is tangent? Tangent is sine over cosine, right? Tangent 3x equals sine 3x over cosine 3x. Similarly, tangent 5x equals to sine 5x over cosine 5x. So if we rewrite this out, because we're dividing, we will have sine 3x times cosine 5x divided by the denominator would be cosine 3x, then sine 5x. Oops. Sine 5x.
Excuse me, where did you get 5x?
You see the angle tangent 5x?
Oh, sorry, got it.
Yeah, they should put parentheses. Sometimes this causes confusion. So this means the trig function, the angle is 3x for the numerator. For the denominator, the angle is 5x. That's why I put parentheses around. So when you use this definition of tangent is sine over cosine, you have this. So this becomes sine 3x cosine 5x divided by cosine 3x sine 5x. Now we have sine 3x in the numerator, so we need 3x in the denominator. So we multiply 3x over 3x, right? Then we're left with 3x. We're left with 3x in the numerator. The sine 3x over 3x becomes 1. Then cosine 5x in the numerator. In the denominator, we have cosine 3x. Sine 5x, we need 5x in the numerator, right? We want to multiply 5x, sine 5x, no. We want to multiply 5x over 5x to 1 over sine 5x, because this is in the denominator. Then 5x divided by sine 5x, take a limit when x approaches 0, becomes 1. So we have 5x in the denominator. Now simplify x with x, right? So this simplified to be x is gone. We have 3 cosine 5x divided by 5 times cosine 3x. Now x is in the domain of the new function, right? Because 5 times 0 equals 0. What's cosine 0? 1. So in the end, we have 3 over 5. All right, that's a lot. But if you're confused, you can, be watching this, because I record this course. And do your homework, okay? Okay, someone wants me to explain one more time, but I have another class. Let's see. So basically, you use the definition of tangent. The tangent equals sine over cosine of the same angle. Then you use the identity we talked about before. Limit x approaches 0. Sine x over x raised by an integer will be 1. All right, then do step by step. Okay, I'll see you Thursday. All right, do your homework. If you have any questions, we'll review the material and we'll talk more about.
You're putting the homework on announcements, correct?
No, I'm not putting homework on announcement. It's in normal learning. So let's see, today we finished this section, right? So you should just do the homework regards this section.
Okay.
Okay, if you are advanced, I already see some students maybe advanced, you can keep going, right? You can go even do the homework before we talk about it. All right, thank you. See you Thursday.
One more question, I'm sorry.
Quickly. I have another class.
Where can we access the recorded videos?
Oh, you don't know how to do that? Let me see if I can show you. Okay, right before you click in join the before you get into the classroom, let me just let me stop recording